In this video, we are going to look at extrema on an interval. So in order to talk about that, we first need to define what we mean by extrema. So let's define those things. We have two different types of extrema that we might encounter, at least two different types of relative extrema that we might encounter. Extrema, we're really just thinking about extreme values. Right? So if there's an open interval I containing C, so we have this interval, and somewhere inside this interval there's some number C, where the function value at C is greater than or equal to all of the other function values in that interval, then f of C is a relative or local maximum, right? So if f of C, our function value, is larger than all the other function, or at least as large as all the other function values around it, we will say, relatively, this is a maximum. It's a relative maximum. Or locally, it's a maximum. It's a local maximum. And we can define the same kind of thing for a minimum. If there's an open interval I containing C, which the function value at C is less than or equal to all of the other function values in that interval, then we say f of C is a relative or a local minimum. So let's draw a quick graph just so we can view what these things kind of look like. So let's say we have something like that. We will have a relative maximum right here at this point. That's a relative maximum. Everything, all the other function values around it are smaller than it, are less than or equal to that. You also have another relative maximum up here relative to the other values around it. It is a maximum. We have two relative minimums in this graph as well. There's a relative minimum here. There's also a relative minimum here. So that's what we mean by relative max and relative min. Now, there are some observations that we might be able to make regarding the derivative at these relative extrema. Okay, so what do we notice about the derivative at the relative extrema? So let me draw a new graph. I'm going to do some stuff that's maybe a little bit different than... Let's say we have something like that. Let's look at where we have relative maximums and minimums, and let's see what is true of our derivative at those points. So we have a maximum here, a relative maximum. What is the derivative of that? Well, the tangent line there, right at the tippy top of that, is going to have a horizontal tangent line. Remember, the slope of a tangent line, that is the value of the derivative at that point. If it's horizontal, then the slope is 0. And so, when we have a relative extrema, our derivative looks like it might be 0. If we have a relative extrema, then the derivative is 0. Now you might notice that right up here, we do have a relative max right there at that peak. We have a relative min down here. What's our derivatives at those 2 points? Well, those are sharp corners. So because those are sharp corners, our derivative does not exist at those points. Oh, but we do have a relative maximum there. So the derivative is 0, or that derivative does not exist. So one of those two things is going to occur if we have a relative extrema. So these places where the derivative is 0 or where it does not exist, we give that a special name. That special name is a critical number. So let's let f be defined at some value c. If the derivative is 0, or if it's not differentiable at c, right, so the derivative is either 0 or does not exist, then c is a critical number of f. So let's look at this example. Find all critical numbers of this function, f of x equals 4x over x squared plus 1. So how are we going to find those critical numbers? Well, first we're going to take our derivative. This, we will have a derivative that's going to use a quotient rule. So we have low d high minus high d low, square the bottom, and away we go. So that is our derivative. Let's go ahead and clean it up. So that numerator we have 4x squared plus 4 minus 8x squared. So we would have negative 4. Oh, actually, let's write this as 4 minus 4x squared over x squared plus 1 squared. So that is our derivative. Now we haven't found the critical numbers yet. How do we go about finding the critical numbers? Well, to do that, we need to set this derivative equal to 0. So when will this be equal to 0? It's going to be 0 if the numerator is 0. So we have 4 minus 4x squared equals 0. That is going to happen when x squared is equal to 1. And so x is plus or minus the square root of 1. So x is equal to plus or minus 1. So those are critical numbers. Those are only the places, though, where the derivative is 0. We should also check to see, is there anywhere where the derivative fails to exist? Right? So our derivative does not exist. For this, we have a rational function. So this derivative won't exist if our denominator is 0. So if x squared plus 1 squared is 0. So if x squared plus 1 is 0, which would be x squared is equal to negative 1, and that's not going to happen. There are no real valued solutions. X would be plus or minus I, but we're only interested in the real valued solutions. So what are the critical numbers here? Our critical numbers are negative 1 and positive 1. And what do those critical numbers tell us? Those are possible locations of relative maximums and minimums. Right? In our next video, we will talk more about those being the potential locations of relative max and mins, and then we'll go through some further examples where we find critical numbers. All right, we will see you there.